Hello everyone, in this video we look into solving equivalences of modular arithmetic. I'm going to start with linear congruences and then move on to a problem related to nonlinear congruences. For solving the linear congruences, we kind of see that type of calculation in the last video already, but now we just kind of form a formula for that, or an equivalence of the form of AX congruent with B mod N. So for a linear congruence is an equivalence of the form. So AX congruent with B mod N, for A and B are integers. X is the variable that we're going to look for, and N is the modulus. But let's start with something simple enough for us to see what's going on. So in the following example, I would like to find the value of X, where X is congruent to 254 mod 8. So for this equivalence, what you're trying to find is value of X such that X is congruent to 254 mod A. Right? By definitions of congruence of mod N, what you can also say in this particular case is that instead of writing this equivalence in this particular form, you can write that what is value of X such that 254 is congruent to X mod 8. So that means that what you're looking for is the remainder of this equivalences. Alright, so to find the remainder, what you do is you take 254, you divide it by 8, and you use a calculator. You should get 31 with a remainder 6. Again, how to find this remainder 6? You can carry out the calculations of the divisions, and you would find out that the remainder is going to be 6. So let's just quickly do that. So 8 going to 25, you're going to get 3 times 8 is 24. Do subtractions here, and you're going to get 1. Or 8 going to 14 at this point, you get 1 times. So 1 times 8 is 8, and 14 minus 8 is going to be equal to 6. So the remainder is equal to 6. Another way to look at this particular remainder is that when you use a calculator, you get 31. What you do next is you take 254 minus 31 times 8, and you carry out these calculations. You should get 6 as well, and that is the remainder. And that is what we're looking for, right? For X is the congruent of 254 mod A is equivalent to writing 254 congruent to X mod 8, and we're looking for the remainder in this case. So the remainder is 6, therefore X is equal to 6. Alright, so move on to another example. So the following example is another linear congruence. That is, you want to find X such that 139 is congruent to X mod 13. Right, you see something like this in the last video already, where I write probably 139 congruent to a question mark, because we are looking for the remainder of those calculations. Right, so instead of a question mark, I have a variable X in this case. Okay, so what you do is you take 139 divided by 13, and it's going to be equal to 10 with remainder 9. And to find 9, again, you can carry out the divisions if you want to, or you do 139 minus 10 times 13, and the calculations give you 9. That is the remainder that you're looking for. Thus, the value of X in this case is equal to 9. So the next problem is probably get a little bit more complicated, because you have to do a little bit of manipulations in order to get to the solutions. So in this example, I would like to find the value of X such that 2X congruent to 1 mod 5. So what is the value of X here? You cannot just simply divide both sides for 2, because when you have 1 divided by 2 is not going to be an integer, and that violates the requirement for this type of setup. So what you do is that you're going to set up a table, right? In the table, we're going to have multiple columns here. So the first column is the value of x. And because we are dealing with mod 5, so the value of x that we're going to consider are 0, 1, 2, 3, and 4. Now you calculate 2x, and the next thing you do is you calculate 2x mod 5. Why is that the case? Because by definitions of congruent, what you can write is that I'm looking for the value of x such that 1 is congruent to 2x mod 5. And see if when you do 2x mod 5, any 1 will appear in this column. And if there is 1, then you have the value of x to be the solutions of the calculations. So when x is equal to 0, 2 times 0 is 0. So 0 mod 5 is going to be 0. 1 times 2 is 2. 2 mod 5 is also equal to 2. Now 2 times 2 is 4. 4 mod 5 is 4. And 3 times 2 is 6. 6 mod 5 is going to be 1. That means that when you take 6 divided by 5, the remainder is going to be 1. Now for number 4, when x equal to 4, 2x equal to 8. You take 8, you divide it by 5, and the remainder is going to be equal to 3. And there is only one solution where 2x mod 5 is equal to 1. And therefore, you conclude that the solution is x equal to 3. Now, if you extend this value of x to 5, 6, 7, 8, 9, 10, so on and so forth, you will see a parent will come up. Right? So when x equal to 5, eventually you're going to get 2x mod 5 is going to be 0. When x equal to 6, 2x mod 5 is going to equal to 2. When x equal to 7, 2x mod 5 is going to equal to 4. And when x equal to 8, 2x mod 5 to go back to 1. Alright, so if you extend the value of x, you will see the parent appear. But because we only consider mod 5, therefore the unit digits in mod 5 is going to be only 0, 1, 2, 3, and 4. Now I'm going to move on to another problem. So in the next example, I would like to find the value of x such that 3x plus 2 is congruent to 1 mod 5. Okay, so what you do is very similar to the last example that we're going to consider a few value of x, calculate 3x plus 2, and then we're going to find 3x plus 2 mod 5 to see any remainder is equal to 1. Then the value of x, where you have 3x plus 2 mod 5 congruent to 1, will be the solution. So here's going to be the table again. So you have a table here, x is going to be from 0, x is equal to 0, 1, 2, 3, and 4. Then you have 3x plus 2, then you do 3x plus 2 mod 5. When x equal to 0, you have 3 times 0 plus 2 give you 2. So 2 mod 5 give you 2. When x equal to 1, 3 times 1 is 3 plus 2 is 5. Then 5 mod 5 is equal to 0. Next equal to 2. 3 times 2 is 6 plus 2 is 8. Then 8 mod 5 is 3. Then you have 3 times 3 is 9 plus 2 is 11. 11 mod 5 is going to be equal to 1. And when x equal to 4, 4 times 3 is equal to 12 plus 2 is 14. And 14 mod 5 is equal to 4. So this side is going to be the remainders. And as you can see, you have this to be the results, right? So the remainder is equal to 1. Therefore, the value of x is equal to 3. So that means when x equal to 3, 3x plus 2 is congruent to 1 mod 5. Right, so we're going to move on to another example. In this example, you're going to have 4x plus 8 congruent to 20 mod 6. So that is, you want to look for x such that 4x plus 8 is congruent to 20 mod 6. So 20 mod 6 is that you're going to take 20 divided by 6, and you're going to get 3 with the remainder of 2. So this is equivalent to doing for x plus 8 congruent with 2 mod 6. And now at this point, you can form a table and do exactly what you did in the last few example. But in this case, you have mod 6. That means the value of x you need to consider is going to be 0, 1, 2, 3, 4, 5. So here's the value of x, 0, 1, 2, 3, 4, 5. And here in the second column, you have 4x plus 8. And in the last column, you can do 4x plus 8 mod 6. Why can we do this? Because by the definitions of congruent, this equivalence can be written as 2 congruent with 4x plus 8 mod 6. Alright, so let's do the calculations now. When x equal to 0, 4 times 0 is 0, plus 8 is 8. So 8 mod 6 is going to give you 2. That means the remainder is 2 when you do 8 divided by 6. Then you have x equal to 1. So 1 times 4 is 4, plus 8 is 12. So 12 mod 6 is going to be equal to 0. When x equal to 2, 4 times 2 is 8, 8 plus 8 is 16. 16 mod 6 is going to be 4. And when x equal to 3, you have 3 times 4 is 12, plus 8 is 20. 20 mod 6 is going to be 2. Right, that means the remainder is going to be 2 when you do 20 divided by 6. And then when you have 4, 4 times 4 is 16, plus a is going to be 24. 24 mod 6 is 0. And then when x equal to 5, you have 5 times 4 is 20, plus a is 28. 28 mod 6 is going to be 4. Therefore, there are 2 solutions in this example. That is the solution when x equal to 0, because when x equal to 0, 2 is congruent to 4x plus a mod 6. So that's the remainder is equal to 2. Another solution is x equal to 3, because when x equal to 3, the remainder is also equal to 2. So there are 2 solutions. X equal to 0 and x equal to 3 are the solutions to the equivalence. In the next 2 examples, I'm going to carry out the calculations for the nonlinear congruence. So for this example, I have x squared congruent to 21 mod 9. So for congruent for 21 mod 9, 21 is greater than 9, so you need to reduce that number to something smaller than 9. So what you do is that you do 21 divided by 9, and you're going to get 2 with the remainder of 3. You have x squared congruent to 3 mod 9. And then you're going to set up the table and calculate the value of x. When you set up the table, the value of x is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8. So here's the value of x. Here's 0, 1, 2, 3, 4, 5, 6, 7, and 8. So here you have x squared, here you have x squared mod 9. And again, how can I get this particular statement? What you do is you can rewrite this as 3 congruent with x squared mod 9. Alright, so let's do the calculations. When x equal to 0, x squared equal to 0. So 0 mod 9 is 0. 1 square is 1. 1 mod 9 is 1. So 2 square is 4. 4 mod 9 is 4. 3 square is 9. 9 mod 9 is 0. When x equal to 4, 4 square is 16. 16 mod 9 is 7. 5 square is 25. 25 mod 9 is also equal to 7. And 6 square is 36. Mod 9 is 0. 7 square is 49. 49 mod 9 is 4. And a squared is 64. 64 mod 9 is equal to 1. But what you're looking for is the remainder equal to 3. And you don't see any value of 3 here. Therefore, the conclusion is that there's no solutions for this equivalence. Now let me do another nonlinear congruence. In this example, I want to do x cubed plus 3 congruent to 9 mod 4. Again, 9 is greater than 4, so we want to reduce that number a little bit. What you can do is you take 9, you divide it by 4, and you're going to get the remainder of 1. Or you can write x cubed plus 3 congruent to 1 mod 4. Or you can write this later. It's going to be helpful for us to set up the problem. You're looking for x such that 1 is congruent to x cubed plus 3 mod 4. Now you're going to set up the table, and you have some value of x where x is equal to 0, 1, 2, and 3 because we are working with the modulus 4. So here's the table. Here's the value of x. Here is x cubed plus 3. And here is x cubed plus 3 mod 4. X is equal to 0, 1, 2, and 3. When x equal to 0, 0 cubed is 0 plus 3 is 3. So 3 mod 4 is 3. When x equal to 1, 1 cubed is 1. 1 plus 3 is 4. So 4 mod 4 is equal to 0. Then 2 cubed is 8 plus 4 is 11. And then 11 mod 4, 3. And then 3 cubed is 27. 27 plus 3 is 30. 30 mod 4 is equal to 2. As you can see, there is no value of 1, or there's no remainder that is equal to 1. Therefore, in this example, you also conclude that there is no solutions to the equivalence. And that's it for solving equivalences. Right. We look into problems related to linear congruent and nonlinear congruence. So that's it for me. Please let me know if you have any questions. Thank you.